Hello everyone. Hope you had a good lunch. I'm Jagadish from Robin.io.
I am Dhanashankar from Robin.io.
So today we're going to present on stateful apps on Kubernetes and how we can simplify deploying them. We're going to look into the whole how do we deploy and how do we manage the whole life cycle of the stateful applications on Kubernetes. First, we'll see what stateful application is to see what are the components of it, why is it a little bit challenging to run on Kubernetes. Then we'll see containers and Kubernetes and how what's the ecosystem for running stateful applications. Then we'll see the data management, as we all know of, for stateful applications and what are the challenges, and then we'll present some solutions for those challenges, and then we'll squeeze in a short demo on how we simplified running this stateful apps on Kubernetes. So a stateful application is nothing but an application which saves a state for it to be used later, or it wants to share the same state to another application. So it involves persistent storage for that application. So if we want to categorize, let's see all the applications we all know of. And initially we have the web apps, which all Node.js and WordPress. Next we have the SQL databases, where we have the MySQL, Oracle databases, MariaDBs. Then we go to the next step, we have the NoSQL databases, which are the Cassandras and MongoDBs. Next, we have the big data applications. We store a large amount of data, like Cloudera, Hadoop, Elasticsearch. So if you have to categorize them into stateful and stateless, stateless applications are the ones which are the web apps, and the rest of all store some kind of data. And as far as Kubernetes is concerned, the ecosystem is very well matured for stateless applications. But the stateful application is still evolving, and with this where we are trying to see what are the challenges and how we can solve them to bring a lot of stateful applications like the databases, whether SQL databases or NoSQL databases into the Kubernetes. So traditionally, how are these stateful applications being deployed? Traditionally, we used to have a server, and then we used to run an app on the server. This kind of deployment was good. Basically, the servers, we used to name the servers. It's kind of like a pets concept, and they are very specialized. But there are some little issues with this, because there's no resource isolation. If I am running multiple applications on these servers, there was no resource isolation. Thereby, I was not able to provide the service level guarantees for those applications, which resulted in low use of resources in the traditional model. Then came the containerized virtualized deployment, wherein we are running the apps on the guest virtual machines, and the guest OS running on top of them, and we are running apps on top of them. There is some kind of resource isolation, and it also consolidated the resources. Multiple apps were running on the same physical hardware, and it resulted in better CPU utilization. Yet virtual machines are still not lightweight like containers. They still take a lot of many seconds, minutes to boot up. And basically then came the containerized deployment, which we are looking into. Traditionally, we always had monolithic applications. Now in the containerized deployment, a monolithic application is broken down into multiple subparts, subcomponents, wherein you are running each one as a service, and all the services together give the application functionality. And these services are running independently on multiple machines. They talk with each other through the network. They have well-defined APIs, and these services can come down and come up at any point of time independent of other services. This model brings agility to the whole application deployment process, and containers are all lightweight processes, lightweight entities, wherein the whole runtime is embedded in the container, and you can run it on any machine, and they are easy to bring up. They come in a couple of seconds and then go down, and they're very nimble in nature. So with this deployment model, the applications, when you come from the traditional applications to the cloud native applications or containerized applications, the deployment model becomes a little bit simplified for upgrading or providing new features to the application. So how do we run these applications, containerized or cloud native applications? Kubernetes, as you know, in the couple of last few talks here, it has become almost one of the most popular platform to run containerized workloads. All the containerized workloads is very easy to run. It provides all the primitives. It's an extensible platform. It has storage classes so that you can implement your storage allocation and give it to the pods. And as we know, the pods, we already talked about pods in the previous ones, where pod is a set of containers which actually share the network namespace. It also Kubernetes also provides a way for deployments. How can you upgrade the deployment? How can you do health checks of a particular container? If you want to do a replica of a container, you just have to change one variable and update to the Kubernetes. And also, it brought a lot of options to deploy, like canary deployments, blue-green deployments, wherein you can configure how much traffic goes to one container as opposed to other containers. And also, since the containers are lightweight, it results in consolidation of all the resources, and multiple applications are being consolidated into the same physical servers, resulting in the better utilization of resources. So now we have seen what is the stateful application, and we have seen what Kubernetes is, and then what does a stateful application look like in Kubernetes? How do you deploy a stateful application in Kubernetes? So traditionally, you have a server running. You must have installed using the yum or RPM, and then you have a server with application running, and the disks are attached or through NAS or SAN, and then you run the application there. In cloud native, what we are saying is we'll have the same thing. We need a compute, memory, and then the storage. But the application is actually abstracted out so much that the following all terms. How do you connect to the application? We can abstract it out to the service, and then the config map. You can get all the configuration information regarding the application abstract out in this particular element, and you have the secret. What is the secret? Secret to the database, and then you have the deployment and other objects. There is a lot of objects which you can use to compose a stateful application on Kubernetes. This is a simple app like MySQL, wherein you have all these objects. How do you actually deploy it? Either multiple options. One is YAML file. You can use the particular objects to compose your application and give it to the Kubernetes API server, and it's going to deploy the application for you. It's up and running. Or you can use the Helm chart, which is customizable. For example, this is one example of where this is a YAML file. Whatever constructs we have seen there, we see a deployment, and we have the containers, and then we have the storage at the bottom, wherein you compose the application in such a way, and you give it to the Kubernetes, and it's going to deploy the application. This again, we are still talking about MySQL. Now come to the next level of complexity, which is a Cassandra application, wherein it has inbuilt replication, which has partitions, and each partitions can be replicated among multiple nodes. And this kind of application, which is running on multiple nodes, the Kubernetes, basically what makes it complex a little bit, a lot of volumes are there, and they have some dependency, but the volumes are dependent on each other. One is a replica of another. There is some relationship, and it's running on multiple nodes, and there's a large data involved. So if you want to compose the same kind of application on Kubernetes, this is what it looks like. There are multiple objects running there. Each one is like a pod, like compute part, and you have a PVC storage, and then the password, and rest of all is your stateful sets, config maps, network policy, secrets, services. So this is the kind of elements we have to use to basically compose an application in Kubernetes for Cassandra. So let's see what are the challenges one by one. What are the storage allocation challenges for a stateful application? Because it needs storage at some point of time, right? So let's say for a Cassandra, wherein you need 3 disks, which are supposed to be in 3 different nodes, and the storage stack somehow allocates all of them on the same disk, then it's a problem, right? So it's still not fault tolerant with respect to disk. So how do we fix it? we basically allocate them in separate disks, which what we are coming to the point is the storage stack has to be aware of the provisioning requirements for the application. It knows that these are the volumes allocations which are coming, and they need fault tolerance with respect to disk, with respect to nodes, because that is what the Cassandra application is expecting. Now, let's look at another allocation challenge. Let's say you have a MySQL app and you have a redo volume and then data volume, and you have a pool of storage, and you allocate the storage on the same disk. There might be some performance issues. Your log and data volume are co-located, and there might be issues with performance. How do we fix it? We put it on separate disk. Maybe you can put a redo on the SSD, which is faster. So here again, another dimension is coming, which is the characteristics of the IOs, the performance. One is latency sensitive, another is bandwidth intensive. So there we saw fault domain. Here we are seeing the performance requirements. So these are the challenges we see in Kubernetes when you're allocating storage. Normally also we have them, but what we need here is application-aware storage provisioning for Kubernetes, so that whenever a storage is allocated in Kubernetes for a stateful app, it understands each and every volume and what are its fault domains, either it be a disk, node, rack, or a data center, and allocates them appropriately. So application-aware provisioning is one of the solution to these problems. Let's see what are the other problems in Kubernetes. It's not real problems, it's basically limitations in stateful applications. So you have a big app, distributed app running on multiple nodes, maybe 12 to 16 nodes using multiple disks. Any disk can fail, server can fail. Is the application still resilient? The second thing is data must be protected and secured. Right? We all take snapshots. We want to preserve some state of the app most of the times, so that we want to revert back whenever we make a mistake, or if it's a corruption, or application corrupted something, right? So we need some kind of protection, and also we want the whole data to be encrypted. The third one is, if you're packing all the applications on a set of resources, like as you are seeing, this compute has been increasing in capacities, and then the storages are very dense. So a lot of applications are being packed on the same hardware. So if multiple applications are being packed on the same hardware, how do you isolate their performance characteristics? You should be able to specify the SLAs for each application, so that you avoid the noisy neighbor problems. And for Kubernetes, it stops at the CPU and memory level. It doesn't go near the storage, since it doesn't implement the storage. And let's say you have an application, and you have a big application writing lots of data to the disk, and you want to share that application with someone. Will you be able to clone the whole application easily, so that it can be usable by a different team, or you want to try any updates or something like that? So if you are not able to do all these things natively on Kubernetes, it results in lower productivity. Then we all know that the cloud vendors are eating enterprise market a lot, right? So how do we make the applications nimble enough so that you can take the application from one on-premise infrastructure to the cloud? What are the primitives needed? Kubernetes natively doesn't provide any primitives like that. So if you don't have that, you'll end up with the infrastructure lock-in, and then you won't be able to use the benefits all the cloud vendors provide. So these are all the challenges, many challenges for stateful applications. Let's take this application, same challenges, and put in some other distributed app which is complex enough, and see how they fit in. Here we have a 12-node cluster, Cassandra, having 3 replicas running each other, IOs are going on. How can the user preserve the state of an application if he wants to try some operation? So that if he makes a mistake, he wants to go back. Or he wants to move this application to Kubernetes in the cloud. How can he do that? So typically, who are the users of this application? Usually the users of this are the application engineers or the DevOps engineers, wherein they want to deploy the application and run their business logic on these applications. They are not storage admins, They are not infrastructure admins. All they need is a Cassandra application, and they want to run their own application. So what they know is generally a version control they use for checking their code. A simple version control which does everything, like taking a snapshot of an application or any number of times of such a complex application. If they're able to do with a simple command, their productivity will increase a lot. So here, as we see, so they only know of how to check in the code. They all know of the Git as a version control system. We all know that. We basically commit the code. If you want to revert back to a branch, you can go back to a particular commit, and you can take a branch. You can check in the push the commit to a remote repo, or you can clone from the remote repo of your code. These operations are very simple in nature, and all developers use it. So since the applications are used by the application engineers, it should be as simple to do all these operations on a complex apps, like any stateful apps, wherein the apps have some kind of data associated with that. Can we do all those things? So let's say if you can manage the app as if it's a Git, you should be able to, let's say you have a database app with there's a lot of data. You should be able to take snapshots of the entire application, just not the storage volumes or any other pods, whatever we have seen, but the entire application. You should be able to, if you can take a snapshot of the simple commands, then it would be very simpler. And if you have the snapshots, how would you use them to roll back, in case you want to roll back the application to? And then how can you create clones out of it, thin clones out of you want to spin up an application based on a particular snapshot. You should be able to create an application with a single command, which is based on this particular snapshot without moving a lot of data. And you have an application now which you have already taken a preserve the state. How can you move this state and make it live, light it up at the cloud? So it has to be very simple for them, like git push commit, it goes to the remote repo. Same thing, the similar experience, if you can provide to the entire application, it becomes very simple to run stateful apps. So once you have in the cloud storage, you should be able to import them from the cloud, instantiate an app from the cloud. So how do we achieve all this kind of functionality easily with Kubernetes? We're going to see a little bit on how we do it in demo. The same thing, we'll take an application, we'll do one command or one click, and it is going to snapshot the entire application. So how does Robin do? What are the elements we have designed to come to this state? Dana is going to cover the Robin architecture.
So I will give you an overview of the Robin architecture. Robin takes standard Kubernetes and uses it as a pod deployment engine, right? To that, we add an app-aware storage, like Jagdish talked about. Like, what is the need for the storage to be aware of application and volume semantics, right? So Robin adds these app-aware storage. This storage contains provides all the standard enterprise features like encryption, compression, quality of service guarantees for individual volumes, data rebalancing, thin provisioning, and all that, right? We also provide a virtual networking stack which provides features like persistent IPs that some legacy applications still need to run on Kubernetes. We also provide features like VLANs and overlay networking to handle the complexities of the underlying network layer. On top of this, we add an application workflow manager, which uses the storage, compute, and virtual. We combine the storage, compute, and virtual networking elements together, and provides a one-click deployment and that lifecycle management operations for complex stateful applications, right? So, like as Jagdish was saying, like if we want to do all these operations in a very simple way, and we have to take away the complexity of all these operations, and the Robin architecture, the application workflow manager attempts to do all of these things for applications. So now let's see a little bit into how we do that, right? How does Robin integrate with the existing Kubernetes cluster? Our Robin software deploys as a let's say you have a cluster of Kubernetes cluster consists of multiple nodes. Robin deploys as a daemon set on these cluster, which means that like there's a Robin software which is running on every node, right? And users can specify which of the hardware resources like this, which disks should be used by the Robin storage, right? And once the user has given us that input, like Robin basically sets out a container-aware scale-out storage solution, and Robin registers a storage class with Kubernetes, and using which it's able to provide persistent volumes to the pods which are deployed on the nodes, right? These pods have all the interface. They look like regular storage pods that are deployed for any application, but and underneath, like Robin, the Robin software is able to provide the software features to make it all seamlessly integrate with Kubernetes, right? So what does Robin do? Like Robin takes these persistent volumes and it chunks up the logical address space of a persistent volume into fixed size slices, right? And when an IO request, when a write happens on a particular logical offset, a slice is mapped to one of the physical devices. Right? Not that like when a slice is mapped to a physical device, like we don't really make any storage reservation. We just say that like this particular logical slice of a volume goes to a particular device. This is important because like when we do this allocation, the Robin application manager is already aware of what application is being deployed. For example, in the Cassandra case, if you look at it, like we say that like there are each Cassandra pod has a data volume. And the Robin application manager is aware that these data volumes of the Cassandra pods can store replicated blocks, right? And so we know that like these volumes should not end up on the same devices, right? So when we allocate a slice, we ensure that two slices of two different data volumes of a Cassandra application do not end up on the same physical device. So we physical device or physical node as per the fault domains requested, right? Let's say that like in the MySQL example, we know that like the log volume is a latency sensitive volume, right? So the whole application performance depends on the performance of the log volume. Whereas the data volume is actually a batch write throughput intensive workload, right? So we allow the users to specify these volume characteristics when they define the application in the application specification, and the workflow manager takes into account these requirements of the volumes and make sure that like the volumes are allocated accordingly on the storage devices. We ensure that like a latency sensitive volume does not sit on the same device as a batch writing throughput intensive volume. If you notice this, so what we see here is that like when we take an application, we can say that like if the storage stack provides certain primitives such as like an affinity set and an anti-affinity group and affinity set, then we can say that like okay, so these set of volumes have an affinity towards each other, or this volume has an affinity towards a particular node or a particular pod, then we can make sure that those are placed together. And we can also define an anti-affinity specification across different volumes so that like they do not share the same device, right? And we are able, and we extend the application specification to be able to specify, for the user to specify these characteristics of their application for any application, so that like our application workflow manager is able to basically take this specification and push that information down to the storage stack to enable the storage stack to deploy these applications in the correct way so that the application assumptions are satisfied. Now let's look at like how we provide the other lifecycle management operations like snapshots and clones, right? When Robin formats a device, we divide the device into fixed contiguous chunks called segments, right? So each of these segment is a log structured. It writes data in a log structured format. Right? So each segment in this example it's 32 MB. Each segment, like when you write to a particular offset, the slice is like mapped to a particular device, right? And when the data is to be written to that slice, a segment is allocated and it is written. It's written on disk. Each segment is like self-contained in that like the data and the metadata for the segment are written together. So let's see like how an IO is handled in the Robin stack, right? The Robin software like exports the storage for these for the Kubernetes pods as a block device. We make it available on that node because pods assume that there is local storage available, like the storage should be locally available on that node. We make we expose ourselves as a local storage, as a block storage on that node, right? And the application manager like formats the file system as required by the application and mounts it into the pods. When the pods write to the file system, the I/O request comes down through the file system to the block interface. At this point, the Robin software running on that node has control of the I/O request, right? So we can apply data transformation, any data transformation that we want on that I/O request, like encryption or compression. We can also tag the I/O with some metadata, such as like the priority of the volumes and the current snapshot ID of the volume and all, and we send and we redirect the I/O to the node where the storage for that particular volume comes from. It can be multiple. The I/O for the storage for a particular volume can come from different nodes, right? Different devices across multiple nodes, and based on the slice based on the logical offset of the I/O, it is redirected to where the slice is mapped, which device it is mapped to, right? So this architecture provides a bunch of advantages for us. We are able to provide end-to-end QoS enforcement. We are able to provide application-aware data placement, and we are able to provide we are able to utilize storages across different nodes and across different physical nodes to be able to provide storage to any node across the cluster. Now, because the I/Os are written into segments, at any point in time, we are able to draw a line across all the slices of all the volumes of an application and say that like this is a snapshot. Because like each segment is associated with a snapshot ID, and when we see a particular I/O which is of a higher snapshot ID, we'll write it to a new segment. So at any point in time, like without coordinating across different nodes, we are able to draw a line and say that like there is all these segments across these slices form one application consistent snapshot, right? And at any point in time, we are able to go back to to a particular snapshot, and almost as if like we are able to go back in time to the in the I/O stream where for the particular application and go to that snapshot. So, but note that like a Kubernetes application is not just storage, right? A Kubernetes application has, as Jagdish explained, has a bunch of different objects, right? So let's say like you take a snapshot of an application using Robin. It actually takes the information of not only the data part, not only the persistent volumes, but it also takes the information about the current state of the config map, the secrets, labels, etc., which all form the configuration of the application. Along with that, we also save the metadata state of the specification of the pods, the stateful sets, the services, and all that. Together, these three things together combine to form one application snapshot in Robin. Now, when you roll back an application, let's say that you made some configuration changes, or like you made there was a user error, and you want to go back, we roll it back to the previous state with where the data, the configuration, and the metadata is in that state. It's almost as if like you went back in time to the time you took the snapshot, right? And once you have taken the snapshot, we are able to save this entire configuration, all the data, config, and metadata together to either a local backup target or to a remote cloud target. And we do it with one command, so that the complexity of maintaining all these objects is like taken away from the user, right? And once all these things is in the cloud, we are able to restore this the entire application either to the same cluster or to a different cluster. Like it could be a different Kubernetes cluster. It could be a cluster which is spun up, a Robin cluster which is freshly spun up on the cloud just for this purpose, right? Because the backup, because the snapshot is entirely self-consistent, it has all the information required about this application at that point in time. We're able to spin up instances anywhere without dependency, without not needed that like it has to be it can be restored only on that particular cluster from which where the application was originally run. So consider using these, like let's consider some cases where these primitives like makes our DevOps teams and application development teams much more productive. Now let's say that on-prem, like you have, say let's say there's a team, let's say in the US, which has an application which is running, right? And they are developing this application, making changes to the business logic, and they are trying some things. And at some point, they are like, let's say towards the end of their day, they take a snapshot, and then they are basically creating at a known good state, right? Now let's say that like they want to give off this this particular snapshot for testing to a test team. For the development team want to give it out to a test team, they can clone this application and give it to the test team, saying that, hey, so this is a good state. Like we achieved a particular milestone. We are giving it to your team for like to test this thing, right? So we can clone this and we can take this away. In another example is like, let's say there is a production deployment where like where there are teams where there's an enterprise is using this thing, and there is like production data is stored in that particular cluster, right? But the new developers who are like developing new logic and they want to test it against this data, right? You can just take a snapshot and clone of that create a clone application out of the snapshot and give it to the dev test teams to test it again, to test their logic against a valid production data set, and this doesn't affect the production cluster at all, right? So the other thing is like, let's say once you push this snapshot into the cloud, let's say like at the end of the day, like I am a team in the US is like they have developed that. They have done their work. They want to save it. They push it to the cloud, and then let's say in their daytime, let's say there's a geo-dispersed team, like a team in India, which comes online, and they can pull this application from the cloud, and they can start working on it. They can continue their work on it, right? So these kinds of workflows are like very intuitive, and they help improve the productivity of these teams. Note that like in this entire workflow, the different teams which are involved, or different people who are involved, they are not aware of any of the complexities of Kubernetes at all, right? As we've seen here, like the various objects of the Kubernetes and various the primitives, like there's infrastructure operations like snapshot, backup, all these are actually totally abstracted away from the individual development teams. And this provides a lot of productivity improvements when deployed at the various application teams.
So let's go into each operation in detail. As we are seeing in this slide, the user who's using it is actually writing his own business logic, and he doesn't know anything about volumes or infrastructure, how many pods were running, anything. All he's using is simple commands to spin up an application, create an application from Snapshot, and everything is taken care. If you want to take a snapshot, it's like copying your photo to a drive. It's as good as copying take one push, Robin push SQL app means, and give the bucket name, a GCS bucket name and AWS bucket name. It's going to take the entire snapshot to the cloud store where you can use it. You can spin another cluster on the cloud and use this as a source, and then spin up the application. You just instantaneous light up. So if here we are seeing a snapshot. In this case, we are seeing on the left side we are seeing a Git commit. How simple it is to commit your code into one snapshot. Every commit is basically you have a unique ID in Git, which we can save the state. Same thing for the application. What we're saying is with simple command, you are going to snapshot the entire application. Like we just saw the 12 node Cassandra cluster. Underneath, a lot of things happens. There is a consistency volume group for all the volumes. It also goes and talks to the Kubernetes, what are the objects used for this particular application, and then it takes a snapshot of both of them and then saves them in one shot, which basically becomes an application snapshot. Because it's an application consistent, which means that you have a pre-snapshot hooks and the post-snapshot hooks which you can use to make them application consistent. And as you've seen, everything in this whole entire operations is application driven. Nowhere we are seeing any operations or any commands about volumes. It's all the objects are all applications. It's from the beginning it will be application driven. So once you have taken the snapshot of an application, you can continue to change the application. And if you want to restore because you dropped a table, which will go to how to demonstrate, I will demonstrate that. And we say with a single command, I want to roll back to a particular snapshot which I have taken which was taken in the previous slide, right? It should restore everything, including all the interfaces, everything, all the pods, storage data, everything is gone to the time travel to the previous state in the up and running. Which basically you can use, there's a lot of use cases for this. If you hit a corruption or user errors or you have an upgrade failure, you can go back to the same state. And let's say you add more data. When you took a snapshot and you added more data to the application, and when you revert back to the old state, all the scenarios have to be taken care of. Next, as we're talking about, is a thin clone. Once you have a snapshot, you should be able to create multiple apps out of this snapshot. Not the underneath, basically it is thin volumes which are being created out of this snapshot, but we provide thin clones because the architecture allows basically looking through all the metadata objects and data objects, and then having an application driven architecture allows us to create any number of clones from a particular snapshot, which means that you will be able to do a QoS guarantees on your base snapshot on the base volume. Also, what are the QoS you need for the this thin clones, so that you don't have basically the clones affecting the actual production deployment. And here you can see you can use thin clones. There are a lot of use cases where you want to test your application, new changes, or you want to run analytics on it, or anything you want to generate the reports. You can just take a thin clone out of it and run the reports and then close it. It's like any other application. So now that you have captured the application entirely, how would you want to basically you would like to save that somewhere else in the offsite. We have some redundancy at the data center level wherein we are copying, having multiple replicas and everything. If the whole site goes down, or a server goes away, or it takes multiple servers goes away, you want some offsite copy somewhere, right? This is where pushing your application to the cloud comes into picture. It uses the same concept of application. It pushes all the objects of the whatever snapshot encompasses and then sends it to the cloud. The first one will always be a full copy, and then the subsequent ones will always be incremental copies of this application. So you can use any one of them, like S3, GCS, any object storage, or even an NFS share. You can have an NFS server running on your data center and say I want to back up this thing to push this application snapshot to that particular repo, and we should be able to do that. And everything is basically encrypted and compressed to make it efficient. Once you have something from the cloud, in the cloud, can we basically light up the same application on the cloud infrastructure? All the major providers like Google, Amazon provide some form of managed Kubernetes, wherein you can bring up the application. So you can take this and then say app pull this thing, and it will pull that app from the object store and then make it live on the Kubernetes cluster on any cloud. So this portability is assured because everything is managed through Kubernetes objects and underlying volumes. So let's see how basically we do this in our product, just to give a flavor of how we do this. So this is how it looks like, and we have all applications right now, and let's see if the network is. Hi. I think the network is slow. Okay, let's try one more time. Okay, actually this cluster is running on AWS cloud. So you have bundles here. Basically, the bundles are nothing but an application specifications. Let's say you have a Cassandra bundle. If you want to create an application, typically an application user doesn't know about any storage or anything. He just comes here, and then he opens his portal, and then he creates an application like this. SQ 2 GB, and then there's a lot of other options, but advanced configuration options, but we just do a provisioning application, and now it's going to create an application on Kubernetes with giving all the objects. First, it's going to compose with all the objects we have seen, the pods, config maps, and everything, and it creates a particular storage, and it's deploying on Kubernetes. So once it deploys on Kubernetes, we should be able to we can basically connect to it and then write data out of it, right? So I'm using another application here, which is SQL Pad. It's like a client for to write into this one. If it's possible, we're going to demo how to. Yeah, it's already done. So your database is up in the matter of 40 seconds, and if you So here we have the pod running, and let's say 72, and so yeah, let's use this because it already has 72. So give me a second. So I just can copy and paste for the sake of time. So basically it's going to connect to this particular database and run this. I just want to change the time. Let's see. I didn't create the table as such. Let's see if it gives an error. And now we'll try to create a table and insert into it some entries. So we have a table, created a database, created a table, add some entries into it, and let's go and take a snapshot out of it with some data, and then we'll drop the database, drop the table, and see if we can recover from the snapshot. So here, all we have to do is take a snapshot like this. At this point of time, it is querying all the metadata objects, Kubernetes objects, and then also the data. It's putting a marker on all the volumes of this particular application. In this case, it's Postgres. It can do for Cassandra in any databases which is distributed in nature. It already took the snapshot. and we can go and let's try again. There's still data there, and we are going to drop the database, and so we don't have the table yet. So now the live application doesn't have the data yet. Let's go and roll back to the state where we took the snapshot. So here we already took the snapshot, snap 1, and we are going to do restore to this point. Are you sure? Okay, right? So what this is doing is it is going to do the entire application. We are not changing anything. The application is going to connect to the same application using the same query, and you should get the old data. It's basically trying to, while this one is going on, it is trying to restore the same things, all the objects which is already stored as part of snapshot, checks the differences, what was there before, what was that, and tries to apply those things back. I think, yeah, we should be able to make it for under 5 minutes. I think this takes like 40 seconds. The same thing as this is going on, we can see that other things like we can have Kubernetes versions, and then, okay, close, right? And then we have these bundles here. So basically, you can give your specification of your application specification into these bundles, or this is anything like a Helm charts which people use on Kubernetes. Let's see one of them, like Cassandra. We have taken. Yeah. It's very very slow. It's all connected to the cloud. So when you click a bundle Cassandra, right? So you have you have a seed, a member. There are multiple roles. You can specify all the storage requirements, and if you see here, right, there are more configuration options like what are your placement. Place seed contains different from nodes. So you can give all the specification in a simple language, so that you can create the cluster. So let's go back to this. Okay, so we should let's do this again. We have the data back. So we drop the table, we restore it, and we have the data back. The same thing you can use again. This one, the same snapshot. Application is here, and you have the snapshots there present on that application. You should be able to clone even with the simple command. See, if you have a bunch of snapshots, but you can also configure schedules, which is normal for all our enterprise applications. And then you want to do a thin clone. It's again basically, and it creates a cloned application out of this snapshot. Well, the same thing, if you connect to it, you'll get the old data basically. As this is going on, any questions?
So I think in the architecture you mentioned that you're routing the logic calls from the kernel space to user space, right? So what's the technology, or what do you use to route requests from kernel space back to user space,
Okay.
and then route to your servers?
The question is, how do you route the IOs from a kernel to the user space?
So in Robin, we have a virtual block driver which registers as a block device to the kernel, and when we expose the block device, when we want to provide access to access of a volume to a pod running on a particular node, we create a new virtual block device, and then we make it available as it looks like a local device on that node. Right, and we create a file system, and then we mount it, like let's say ext for XFS, right? So now when the write comes, the driver basically gets our user space does a daemon, like running in the daemon set. It basically talks to the driver and just gets it's just a netlink socket which basically takes the data out of it.
And is the daemon one per driver or a single daemon serves?
Yeah, the single daemon serves the entire node, essentially.
Thank you very much. So you can get the software and try it out. There's a license-free one. So you can try it out, get.robin.io on any of your GKE clusters or any Kubernetes clusters or on-prem clusters. Thank you.